Hello and welcome to Toddcast number 27. It kind of ties together what few things we've done in the two previous Toddcasts, and that was to look at optical rotation for optical isomers. And so this will go into more of the physics of this, but ultimately, in the end, we'll look at how the number that gets spit out by it can tell us a lot of information in terms of our molecules. So, polarimetry and enantiomeric excess. So, I'm going to start with the concept of polarimetry. And so you have to understand what polarized light means. And so our light, we typically represent as a wave. So we have light that goes like this. But that is actually what's known as an electric wave, meaning if you take an electron and bounce it up and down, you'll create this wave, just like if you take a hose with water running, bounce it up and down, you'll get a wave that comes out of it. And so it's the so-called electric wave. Perpendicular to the electric wave is a magnetic wave. Beyond the scope of what we'll do in OChem, but something that you should know as well, just as a scientist in general. And so certain materials, so light naturally, like sunlight, it's random which way it's oriented. The electric wave might be vertical, might be horizontal, might be any angle in between. The propagation direction is random. It goes in all different directions. And so light is random when it starts out. And if we can come up with materials called polarizers, you've dealt with these when you have polarized sunglasses, your screens on your computer, and phones are polarized materials. Some are permanently polarizing, meaning they are polymer that when it condenses down, coalesces together into its final material nature, the fibers might all be vertical like this. That's the most common type of polarizer, the cheap plastic material that does that. It's just the property of the polymers when they bind into a solid. And then some can actually be turned on through paramagnetic induction. So if you have a paramagnetic species, again, that unpaired electron will create a net magnetic moment that can be pointed any which way. But if you put it into a magnetic field, it will align in a very specific way. And when it does this, it creates a polarizing material. And so we are only going to deal with the material type. So basically a chunk of plastic with polarized packing that creates a polymer. So one of the analogies I like to give is, let's say you're out in the ocean minding your own business and you piss off a school of stingrays and a school of halibut. And so we know stingrays go like they quote unquote fly underwater. Their wings are spread out parallel to the surface at the bottom or the top. Halibut rotate that by 90 degrees. They actually swim in a way where their fin and their dorsal side are like a vertical line. And so they are perpendicular to the surface. So anyway, you have these two fish. You have one that's swimming this way, one that's swimming this way. If a kelp bed is up ahead and you see a bunch of kelp, let's say it's all vertical like this, if you swim through it, you will get away. Actually, let me choose a different color. If you swim through it, you will get away from the stingrays just fine. They're going to get caught. They're perpendicular to the seaweed. They won't be able to swim through it, but the halibut will. So a polarizer allows light that has the correct orientation. The electric wave is lined up in such a way that it can make it through the filter. It can filter it out. So polarizing sunglasses do two things. Number one, they filter out some of the light that isn't aligned correctly. In theory, if it's randomized, then half the light gets filtered out. And then number two, it allows light coming through to be oriented in a very specific fashion. Okay, so let's go to our actual subject today, not stingray and halibut escape techniques, but polarized light. So notice this light is random here. So these represent waves. These arrows represent a wave. Like this arrow here and here represent this wave going like this, the one that's shown. Okay, so the light comes through in a very predictable and polarized fashion. We send that light then through a sample. Now, for whatever reason, materials, because of their asymmetric nature versus symmetric nature, if they're asymmetric, they interact with light asymmetrically. If they're symmetric, they react with it symmetrically, interact with it. And so if you have a polar compound, no big deal if that's an electric nature. If you have something that's non-polar, no big deal. But if it's optically active, that's what we're going to look for. If something is optically active, it means it has asymmetry of structure and therefore asymmetry of electron distribution and ultimately asymmetry of its internal magnetic field that it creates from these moving electrons. So if this light interacts with that, these plain polarized light will actually start to rotate, absorb and be sent and re-emitted at an altered angle. I don't want to say absorb and emitted because it's not actually an absorption emission process. It's an interaction process, interaction with magnetic field, and it'll rotate. Okay, so polarized light can pass through another polarizing plate without losing intensity. So if there's a second plate, so I'm going to draw two possible plates. Let's say I draw another plate up here that's like this. So the same sort of plate, it's going to go through just fine. The light will just keep on coming through, no big deal. But if polarizing plate is like this, sorry. If it is perpendicular, then these waves get filtered out. So if you had sideways seaweed, so if you go back to the same analogy, halibut and stingrays are chasing you, you go through the normal vertical seaweed and all the stingrays are gone, but the halibut get through. But then if you could swim through seaweed that grows sideways, if there was something of that nature, then the halibut would get filtered out and you would go through all by yourself. So two perpendicular filters can get rid of all of the light. So basically it's saying polarized light passes through another polarizing plate without losing intensity if it's in the same direction. If, however, it's 90 degrees perpendicular in nature to the first one, then it can filter out everything. Okay, so that's polarized filtering. Okay, so hopefully that makes sense. So here's how we're going to take advantage of that. A polarimeter is going to be that same situation where we have polarizer 1 and polarizer 2. This is light. I'm not going to draw the waves anymore. But if they're both aligned the same way, so if I could take this plate and put it, that'd be fine. But what is really strange is if you have some compound in here, so in this region right here, if I have a chiral species, that was an interesting way to spell that. Sorry, I'm missing a C. But you don't want C's either. So we're on the same page on that. If it goes through, if it interacts with that, the compound can actually rotate it in such a manner. So let's say it rotates it this way a little bit. Then instead of the polarizer being lined up, the second polarizer lined up the exact same orientation, we actually have to rotate it so all the light can get through. So it's really hard to picture, but let's say the halibut that swam through this one started to rotate slightly, then the grid would have to be turned slightly for it to get through. So if the wave is coming through like this, it's not going to get through. But if it starts to rotate, if it goes through this one, and then ends up, I'm not going to do justice with this, but if it rotates enough to get through, then light will be set. So if there's an optically active chiral compound in solution between the two areas, right there, then the second polarized plate must be rotated whatever amount. It'll vary depending on the compound and concentration. And so if I look at this line right there, and then compare it to the line there, that represents how much it rotates. So if I brought those two lines over, move them over there, the amount that this plate was polarizing plate had to be rotated for it to get through is called the optical rotation. That is the magnitude of that angle. Second polarizing plate is the observed rotation, and we call it alpha. Okay, as I mentioned in a previous Toddcast, it matters what wavelength of light you use. So it's got to be monochromatic, single wavelength. We typically use D band or 589 nanometer light. It goes through and the first plate rotates. Every wavelength interacts to a different magnitude. So the amount of rotation would depend on the light used, the concentration of the sample, and the distance it traveled. So to have uniformity so that we compare things across the board, we typically always use the same wavelength of light. We use the same standard distance, a decimeter, and then we use a set concentration. If it's not a set concentration, then we convert mathematically to a set concentration. Okay, so that's a machine itself. So this is hopefully the best justice I can do to how this thing is rotating. And visually, it's really hard to represent, but the wave is coming in perfectly vertical. It comes out vertical, but as it goes to the solution, it's starting to rotate and take on a horizontal component. That's what this is supposed to represent, so that the wave comes out in line with this. So this is rotated ever so slightly. So these lines are not parallel because it had to be rotated to make it work out. Okay, so the first polarizing plate, second polarizing plate, the solution is in here. It's a fixed distance, so I want to make sure, emphasize that it's 1 decimeter in length, and then it rotates light by a certain amount. So this line compared to that line, that's your angle of rotation, and it should be consistent with the picture. So by definition, what we observe, the amount of rotation, we take that and we divide by the length of the sample, which is hopefully 1 decimeter, and the sample, so the grams per milliliter is a unit. We usually put it in a gram and 100 milliliters is your standard concentration, but this is tossed in there just for, the sake of calculation. And we end up with a whatever value. Okay, how we apply the information is what matters. So I've thrown a lot of information at you. The physics, nice to know, not essential for chemistry, but the more you know of one science, the better it can help you understand other sciences. But any sample that rotates plane polarized light is called optically active, meaning it is interacting with plane polarized light, i.e. light, so it's optical, and it's actively rotating it. So if you have a net rotation of light, your solution has chirality. Okay? A sample that does not rotate it, optically inactive, or an achiral solution, has no net chirality. If a pure sample of a compound is optically active, it will rotate plane polarized light. Okay, so just random fact. An achiral compound will be optically inactive, which means it will not rotate it. The measured angle rotation is the observed rotation alpha. The standard one, when we divide everything through, is the standard. So this is the one we measure by. Notice it says lambda. Again, D represents a very specific wavelength. So usually you'll see this as a D representing the wavelength we use, the concentration, and then the length in decimeters. So does temperature matter? Absolutely. We occasionally put a temperature there. It changes the density of the solution, which will change how much the light interacts. So anything that impacts the density, the concentration, and or the temperature play a role. So we typically use 25 degrees, D-band light, 1 decimeter length, and then gram per 100 milliliters in concentration. Hopefully it seems reasonable and okay. So the standard alpha D is what we're going to compare one compound to another. So conventions, clockwise rotative light, rotation of light is given a D, it's called dextrorotatory, given a D as we saw earlier, also designated as plus. Counterclockwise rotation of light, lever rotatory, L, or also given a negative designation. There is absolutely no correlation between small d and capital D, small L and capital L. So in the absolute configuration, R doesn't automatically go with D, L doesn't go with S, it fluctuates. That said, in general, D, a little more often than not, will be positive in R, and L will be a little more negative in S when you have one chiral center, but that's just a small amount. So we have a tendency to have that bias because it happens, but there is no correlation. They wanted one, didn't work out for them. Pure compounds only contain, enantiomerically pure, meaning they only contain one enantiomer, only the R, only the S. So if you have pure 2-butanol, and in this case, R, it'll be negative 13.5 degrees for your optical rotation. And then if you have, in this case, 1, 2, 3, but H is in front, so S, it is positive. So again, this is one of those exceptions of if I try to convince you that R equals positive, S equals negative, this is one of those exceptions. So there is no correlation. So R2-butanol, negative, S2-butanol, positive. You can also then call this negative 2-butanol because it rotates like negative and positive, and you could also call it small L and small d. So small L, same thing as saying negative, the small d, and it should be actually a cursive d, but the small d represents positive rotation of light. Okay, this is where it gets interesting in OChem. Mentioned something called an racemic mixture earlier. Racemic mixture is where you have equal amounts of the two enantiomers. So I'm going to go with a simple case of just an R and S ratio, because that's what we just had, the 2-butanol R and the 2-butanol S. So if we have 100% R and 0 S, it's pure R, then we had a negative 13.5 degree optical rotation. If it was pure S and no R, then we had a positive. If you have 50-50, 50% of each, then you have 0. They cancel one another. So one of the things chemists can do to see how pure, enantiomerically pure a solution is to look at the rotation compared to the perfect or pure mixture. So racemic mixture, 50-50, pure R and a pure S, very predictable. So if you had something around here, then I know it's going to be more R than S. So maybe that's 75-25, 3-to-1 ratio of R to S. And if I have that, then the optical rotation is going to be a linear or weighted average of the two. So half of this, 6.75, so it might be negative 6.75. And then equally, if I went to the other side, move it over here, when I had a 25-75, then it'd be positive 6.75. So from this number here, you can get the purity ratio. And that's usually what we do. This is called enantiomeric excess. Racemic, there's no excess, it's equal parts. Pure is 100% excess of one, 100% excess of the other. But 75 minus 25% would be a 50% excess of R. Forgot to toss in the 25. 75, which would be a 50% excess of S. Okay, there it was. I just needed to be a little more patient with myself. Okay, so 50% excess of the negative, 50% excess of the positive. Okay, so any sample with alpha D between 0 and negative 13 means it must have more R than S. The exact amount will be the amount of percentage of R minus percentage of S. And same thing on the opposite side. Anything between 0 and positive 13 will have an excess of S. And its enantiomeric excess will be some number of the S minus the R. So this is actually pretty useful when we do synthesis. We can find out how stereopure a compound is by looking at optical rotation and comparing to what a pure sample has to figure out how well we did. So that last part is going to be the more interesting part when we look at synthesis down the road. So on the short term, you have to know what a racemic mixture is. You have to recognize that a pure sample compared to an impure sample will have a varying optical rotation. Down the road, you will actually have to look at enantiomeric excess. We do a reaction, and let's say two compounds come together, but it comes more on one side than the other. Then we'll get more of one enantiomer than another, and as a consequence, you'll end up getting an enantiomeric excess that you can use to study that compound. But that covers this. So not a major topic, but hopefully the concept of racemic mixture. And then what a polarimeter does is simply gives me a number to see how much it rotates plane polarized light. So we have finished yet another Toddcast. Hopefully it's going well, and I will see you in the next one. Bye.